Today I'm going to talk about better and faster hyperparameter optimization. Better and faster hyperparameter optimization with Dask and Desk. I'll explain what each of those words mean and why you should care about them. That's not too important right now. The main purpose of the slide is to say the title and say the authors. So I'll be presenting this work. This was joint work with Tom Augsburger and Matthew Rocklin. This was work that I did while collaborating with Anaconda back in 2018. At the time, so Tom still works at Anaconda. At the time, Matthew did too. He does not anymore. So he moved on to NVIDIA. Then he's actually started his own company called Coiled that focuses on Dask, which is why the picture's there. Yeah. Okay. And then of course I'm a graduate student at the, as Pablo said, at the UW Madison. Hopefully that gets done soon. And then if you want to link to these slides, it's at the URL there in the bottom right. So if you go to my GitHub and click on Docs, you'll see those slides.
By the way, I don't mean to interrupt,
yeah.
Scott, but also it's in presenter view where you see two slides. I just wanted to see if that was something that you intended or if it wasn't.
You can see two slides now.
Right, because we see the presenter view with like the time on the top as well. So I wasn't sure if that was something you wanted to.
That is not intended. Gotcha. Let me fix that. Thank you for bringing that up. Okay, now you can see just the plain view, right?
Yes, there we go.
Yeah.
Perfect.
Yeah, that's right.
Thanks. I was operating with the assumption that it was doing something smart, but apparently it's not. All right. So today I'm going to talk about 4 things. So I'm going to talk about the so this is the first step of explaining what the title means. So I'm going to talk about the problem I want to solve. Hint, it's called hyperparameter optimization. I'm going to talk about the tool I want to use. Hint, it's called Dask. Then I'm going to talk some about the algorithm I want to use for this tool and problem. And it turns out this combination of tool, problem, and algorithm can enable new opportunities for this. Can enable new opportunities. The sum of the parts is greater than the sum of the whole, or maybe the other way around.
I think we might already have a question.
Yeah, let's hear.
Arun, I think. Go ahead. You can unmute yourself. It had the lower the hand was raised. So yeah, there we go. You can go ahead and unmute yourself and ask the question if you'd like, Arun.
Oh, I'm sorry. I think I accidentally pressed it.
Oh, okay. I'm sorry.
All right. So then I'll continue, I guess. Right. So yeah, I was going to say that I'll also mention some experimental results that show how well this does. Okay. So let's talk about the first thing. What is the problem? So the problem is called a hyperparameter optimization. Before we get into that, let's talk about what is a hyperparameter. So a hyperparameter is a parameter that cannot be learned from any data. So it's typically given at initialization before you can see any data at all, any data. These are typically used to define model structure. So this might be like the number of layers in your neural nets or the activation function after each layer or something like that. Let's walk through an example to illustrate what a hyperparameter is, so you can speak the same lingo, the same jargon, I guess. So let's say we have some input and output. Here the input x is a single scalar. The output y is a single scalar too. So it's a really simple model. And we want to learn a mapping between x and y. So given a x value of 1, we want to say the y value is probably around -2 or something. Okay. So to do that, let's make our model just a polynomial. So a polynomial of degree d. So let's just say that our output y is just a bunch of weights times x to the d times x to the d minus 1 and so on. It's that equation right there. Here the hyperparameter is d, the degree, right? That is used to define the model structure, and then with that we can optimize and find the right polynomial, but we need the degree d first. Okay, so basically, all right, so what do different choices of d look like? So d equals 1 is just a straight line, right? And it fits the data okay. The training data, it's not great, but it's okay. D equals 7 fits the training data exactly, but that might not be the best choice because it looks a little uneven. t equals 3 might be a little better. Actually, that looks like some balance between the training data loss and the validation loss maybe in the future. However, after we see some validation data, we see that t equals 1 is clearly the best choice, right? So that's what a hyperparameter is. It's something that's used to define model structure. Okay, so that was a simple example. And again, please interrupt me if there are any questions. So that simple example is a lot more complex with modern machine learning. So here's an example of using TSNE, which is this is a paper by some people at Google Brain, and TSNE is a tool to visualize your data. So that is, so let's walk through a simple example. So let's say we have a bunch of 28 by 20 images of handwritten digits. This is the famous MNIST data set, right? And each image is pretty similar, right? Like all the twos are pretty similar, all the threes are pretty similar. However, the features are not truly representative of the images, right? Or I mean, they are, but like they don't represent that all the twos are pretty similar, right? So here so each image is 28 by 28. So that's 28 by 28 is 784, and the features for each of those 784 features is just the pixel value at a particular pixel between. So it's a number between 0 and 1 or something, or actually between 0 and 255. However, we think that all the twos are pretty similar, all the threes are pretty similar, right? So what TSNE does is it collapses those 784 features down to 2 features, right? And after we do that, we can see that all the twos cluster pretty closely, all the threes cluster pretty closely, and all the ones cluster really closely too. And with this, we can actually build a pretty effective classifier, a really simple linear classifier almost. So what I'm saying is that TSNE is a tool to go from many features, in this case 784, down to a few features, in this case 2, which is all really TSNE can be used for. Okay, so that's what TSNE is. However, the first section of this paper called "How to Use TSNE Effectively" is titled "Those Hyperparameters Really Matter." And so what the authors at Google Brain did is they gave TSNE like a hello world, like the simplest thing you could possibly do with TSNE. They said, let's give TSNE data in 2 dimensions, two clusters in 2 dimensions that are well separated. Let's project back into 2 dimensions. Like this is like a hello world. TSNE should knock this out of the park, right? However, so there's a lot of hyperparameters for TSNE. There's like 6 of them, or 3 of them if you consider. And they chose to vary one, something called the perplexity. And if they change that one, they saw a pretty drastic performance. Perplexity has something to do with like the complexity of each cluster, like in some high-dimensional space or something. I'm not really sure what it means, or like good physical intuition. But either way, as they changed this one hyperparameter between 2 and 100, they saw a pretty drastic performance. So it looks like perplexity equals 50 is the best choice here, but I didn't really know that. It turns out there's a lot of, so that's one hyperparameter. There's 6 hyperparameters that matter for TSNE. Only 3 of them, so 3 of them affect the architecture of the model architecture. So perplexity, early exaggeration, and metric all affect the best possible solution, right? This is like the number of layers in the neural net or something like that. The other 3, learning rate, and iter, and inits, they affect finding the best solution. These are important too. Like if your learning rate is too high or too low, you will not find a good solution, or you'll train for eons instead of minutes. So these are certainly important too, but perhaps not as important as perplexity, early exaggeration, and metric. And those are critical. Okay. What questions do you guys have? Okay, I'll take the silent as there are no questions. Again, please interrupt me at any time. Okay, so hyperparameter optimization is just finding the best set of hyperparameters. So that means that finding the best perplexity, the best early exaggeration, the best metric, and saying these are the parameters that you should train the model on for the entire data set. That's all. That's what hyperparameter optimization is. And then, of course, this will take some computation. Like you can't just look at the model and the data set and be like, oh yeah, that's you should use perplexity 25 and metric L1. You can't quite do that. You have to actually do some work. Okay, so that was the first thing I was going to talk about, the problem. Now I'm going to talk about the tool. So the tool I want to use is called Dask. Dask is a tool that natively scales Python. Can I ask how many people are familiar with this? Maybe this wasn't the best method.
I've heard of Dask
right.
before, but I actually don't know what it does.
Got it.
Yeah, I never use it.
All right. So
yeah, I mean, I know, I'm aware of it too. I'm aware of it and looked at the website, but really haven't focused on Plotly as far as like or Streamlit or other applications that are dashboard friendly.
Right.
There's pick from a half a dozen. Dask is one of them, so I'm really interested to see what auto ML capabilities and how that relates.
So,
yeah.
Right. Yeah. So that's perfect then, because so this will be a good introduction to Dask. Luckily, this talk was only made for I think 20 minutes, and I have a whole hour. So I'll play an introduction of Matthew Rocklin talking about Dask. He's the person who has the first commit on Dask. But first, I'll explain what Dask is from a very high level. So Dask is a tool that natively scales Python. So it provides advanced parallelism for analytics, and enabling the performance at scale for the tools you love. And so what does that mean exactly? So let's look at that. So let's say you have some process in your so Dask can scale out to large data sets or up to more computation. So let's say you have some Python process on your own machine that works well with NumPy, pandas, scikit-learn, and you want to scale out maybe to larger data, maybe a data frame that doesn't fit in memory or something. Dask can do that for you, actually really easily. Or let's say you need more GPUs, and because your model is more complex than scikit-learn's linear model, Dask can also manage that really well, actually. In fact, NVIDIA hired Matthew Rocklin to work on just that. And then, of course, it works well on both of those when you have large memory and a lot of computation. So, all right, so there are a ton of tools that do this, right? Dask is not alone in this space. So what makes Dask different? So you could use like MPI or Slurm or something and hack together a solution, but Dask is different in 3 key ways. So first of all, it's easy to use. So if you can read one, so let's say you have a folder of CSVs and pandas. To read that entire folder with Dask, you change one line. It's basically from import pandas as PD to import Dask data frame as DD. That's about it. It's also declarative. So Dask is declarative. So that means that you describe the computation to the Dask. Dask looks at the description and says, okay, what resources do I have available to run the computation? And then it looks around and says, all right, I can run on, all right, I have computers, let's run that computation on those machines. This means that Dask can work anywhere, right? So, or anywhere that is supported, but almost everything is supported. So if you have a tool if you have access to a computer or a cluster, Dask will likely run on top of it. So Dask runs on top of Kubernetes, Slurm, Hadoop, Spark, your own machine, EC2, GCP, Google Cloud Platform. It runs everywhere. If you have computers available, it'll run on top of it. That's really nice. That's really convenient, and that also makes the code that I write a lot simpler. And then the third thing that makes Dask a little different is that it has a really good diagnostics page. This doesn't sound too important, but it is actually it's pretty important because it allows you to functionally very well to inspect the state of your cluster and see what it's doing and how much memory is available and all of that. It's really useful. So that was a brief introduction. A much better introduction will be given by Matthew Rocklin on YouTube. And this is the standard Dask demo. And then if you So same thing. If you have any questions, raise your hand or mention it in the chat, and then Alyssa or Pablo will mention it to me. Can you hear this?
I don't know if we can hear it.
That's troubling. Nothing?
No.
Yeah, not getting anything.
There must be a way to do this.
Maybe under well, you've got that going. Maybe there's like a setting or something somewhere. Let's see.
Maybe a system preferences thing.
Oh, I see where it is. Okay. So when you can stop sharing your screen, or then when you if you click sharing your screen, there is a you can share your Chrome tab, but there's also like a little box that says share audio if you hit Chrome tab.
Chrome? I'm not in Chrome.
Oh, okay. Oh, maybe it's just me, the Chrome tab. So let's do yeah, not that. Go to the share content on the bottom, and then share application. Click that again, and then maybe like restart, like stop sharing and then start again. And then there could be an audio option because I saw one pop up for me when I was messing with it, looking at the settings. So there's like when you hit share application screen, now there is like Chrome tab. Sorry, there's like application window, entire screen, and then like could be a couple other options depending on what other things that you have open. And there could be a share audio on the bottom. Strange. Alternatively, you could paste the video link in the chat, and then we could watch it with our own computers.
Maybe you can say what the guy is saying as you show the video.
That sounds hard.
I mean, they're like subtitles, right? Like, um, that subtitle CC thing. Maybe we can read what the guy is saying.
This is also true.
I think so. I don't know. I don't hear much of anything. I do see the link though in the chat. Maybe we listen to our own. Okay. Okay. Is the S3 an actual Amazon S3 like bucket? Is that what that initial part is meant to be? Like reading data from an Amazon storage.
What was your question?
My question was the initial part of the demo that says S3, is that like reading from a S3 bucket in Amazon?
Yeah, yeah. So it is. That's exactly
Okay.
right. Yeah.
Okay.
I was replying to you earlier, but my audio was turned off, so that's fixed now.
Yes. Okay. Got it. Yes.
And so I was also trying to say when my audio was turned off that that the person talking, Matthew Rocklin, he was the first person to start Dask back in 2015 or 2014. He worked on Dask through Anaconda for Anaconda/Continuum for I think until 2019. And he spent all of 2019 working for NVIDIA to integrate Dask into their library, which they call Rapids. NVIDIA is the big GPU company. He has since January of this year. He started his own company called Coiled, which is again working. He's a consulting company now for Dask, pretty much, trying to expand that. That's also a massive data set of like 12 gigabytes or something. Probably more than that. Memory of one machine. Dask data frame. And its read CSV. The normal pandas read CSV function. Dask data frame. The Dask data frame. The pandas data frame. Pandas speeds. The, the length of the full data frame. Computing the length.
This is data science version of watching basketball.
What was it?
The data science version of watching a game, like basketball, football, with a commentator and things happening.
Yeah. This is exactly that. Am I am I correct in that you can't hear the speaker? Because I feel kind of stupid.
Yeah, no, that's correct. We can't hear like the video
Right.
audio at all.
All right,
so.
got it.
Yeah.
I'm just questioning if like I'm just saying yeah. Thank you. All right, I'll keep playing the video now.
Okay.
Bad rows. Free rides. Tip fraction. Pandas has a lot of nice daytime. But Dask data frame does. Pandas data frames. Operating a data that's larger than memory. Have a cluster nearby. That Dask data frame. To work on Dask generally. And Dask. Dask is. Dask was. Dask is about lower. Dask is about lower level. Dask data frame is a good fit. Spark, Hadoop, big databases. Many people have problems. Abstraction, not instruction. Not as canned. Dask has big collections. With Dask delayed. with threads on our local machine. On a single machine. $256 numbers. Task delayed. Dask. Parallel computing. SQL. SQL, I guess. Task delayed. Yeah. I don't want to talk about that. I want to talk about so I want to use Dask because it looks like a really good tool. I want to build my own custom algorithm on top of Dask. Is my microphone working?
Yes, yes.
All right, perfect. All right.
So we're good to go.
Yeah. So that may have been suboptimal with the subtitles. It seemed to be at least hopefully it was at least a little bit okay. But either way, what I want to do is use Dask to somehow code. So at the end there, he showed like some fairly like non-trivial algorithm for sum for adding numbers together. I want to do that same thing, but now for Hyperband instead, which is or for an algorithm that solves that problem, the hyperparameter optimization problem. So what I'm going to do now is talk about what problem I want, or what algorithm I want to code in Dask and make Dask work well with. First, I'm going to step through some nice things about Dask. Just this was the brief introduction beforehand. So basically, if you have a CSV or a data full of CSVs, you can read it in pandas like this. You can get that same result for every month. For maybe you have, let's say, five years and 12 months of snow data. You can do the same thing in pandas or in Dask really easily. Dask is also declarative, so it works in a whole bunch of places. Hadoop, Sparn, Hadoop, Kubernetes, Slurm, Moab, SGD, HTTP Condor, all of that. And it also has a really good diagnostics page. As you saw earlier, you can see a graph of what's happening. Okay. So now, what algorithm do I want to implement in Dask? So I described the problem I have, the tool I want to use. Now I'm going to describe the algorithm that I want to use. So first, before I do that, let's look at what algorithm is widely used, and let's look at all the advantages of that. So a very popular algorithm for hyperparameter optimization is random searches. Scikit-learn implements the randomized search CV that does exactly this. All it does is it just so for this problem, I have a model and parameters are given to me. I randomly choose what random search does is pretty much what it does. It randomly selects some hyperparameters, initializes the model with hyperparameters, trains to completion, and reports the validation score, and does that probably 10 more times or something. And then says the best set of hyperparameters is the one with the best validation score. So the picture is that, let's say we initialize 4 models and we train all. So then in this, for random search, we train all 4 models to completion, and then say the best model is the one at the top, the one that has the highest validation score. Then with that model, we would say with that best model, then we would train an entire training data set to compute one final model, and then we would score on the testing set exactly once, maybe before the NIPS deadline. Okay. So there are some benefits from this. First, it's very, very simple, right? Like it's almost this for loop is embarrassingly parallel. It works well with Dask. It actually really well with Dask, but it's very, very simple. By that same measure, it's also very easy to parallelize, right? Because it is so simple, right? The one downside is that it doesn't limit the computation, right? So those 2 models at the bottom, they were diverging. The score was getting worse, but we still trained into completion. Why did we do that, right? We didn't have to do that. That if we were running as an EC2, we had one cluster or one machine for each model. This would cost us more because we didn't have to do this, right? We could have stopped these models early. So if we'd stopped the bottom 2 models halfway through, we could save 25% on our EC2 bill. That'd be really nice. Okay. And that's pretty much what we want to do. We want to limit the amount of computation, the number of floating point operations we do. So we want to do some early stopping. So here we want to limit, say the worst half a model is halfway through, right? That'll save 25% of the total computation. That's 25% of the number of floating point operations, 25% of our EC2 bill. That's great. And that's pretty much what the algorithm I chose to implement in Dask ML does. There's an algorithm out there called Hyperbands, which is it's a principled early stopping scheme for random searches. That's all it is. So it's the same as random search, randomized search CV, except it stops some models at some times. That's the only difference. Okay, and this is not a new algorithm. This is described more in this paper by Alicia Lee and Kevin Jamieson. It's a fairly new algorithm. It was only released in 2016 or 2014, I think. Anyways, so I said that Hyperband was a principled early stopping scheme. That means that there are 53 pages of math in Hyperband proving that Hyperband works well in the very general case. That's great. The intuition for why Hyperband works is very simple, actually. It just says that that deciding when to stop models and how many to stop depends on one parameter. It depends on how important the training data is, right? So if only the training data is important, all you can really do is just train all models to completion and report the best model, right? That's all you can do. If the training data isn't very important, the scores are much more important. You want to explore scores for a lot more. If you want to train one model to completion, then maybe you need some very aggressive early stopping schedule, right? So here, let's stop 50% of the models at 1/3 and 2/3 of the way through. And so what Hyperband does is their paper goes through the whole long proof on running all of these brackets in parallel. So, and there's something in computer science called the doubling trick, which just says that if you run all of these in parallel, you won't do too much worse than if you knew the optimal value ahead of time. So what that means is that Hyperband is just, it runs all of these brackets completely in parallel, where they're each configured to take the same amount of work. So maybe I should have had 3 lines on the least adaptive bracket, not 4. But that's the point. Well, you know, what's great, one bracket that has, or one configuration of some subroutine that has training data very important. Another one that has training data very important. One that's only kind of training, training data is somewhat important. And then let's run all of those in parallel. All those early stopping schemes in parallel, that is. So again, this is, all right, so what is this? Oh yeah, I had one slide on, yeah, I'll go to this slide first. So, right, so what are the benefits of this? So the benefits are that it's very simple. It's very easy to parallelize. It's really, it's not quite as simple as randomized search CV. It's pretty much, it is easy. It is pretty much that easy, right? Because it's we initialize a bunch of models, train them all in parallel, and then we stop some models at some times, and then train them in parallel again. That's great. The one downside to this is that our cluster won't be at 100% CPU usage for the entire time, right? Because at the beginning it's completely saturated. We'll see every core will be active and all that. At the end it'll be like we only have maybe 3 or 4, probably actually 6 or 7 models, and we have to train those to completion. But that won't be a ton of models. Then Hyperband has, again, 53 pages of math saying that it limits the computation on search pages, and they have a bunch of math, 53 pages of math justifying it. The main result from all that math is given on this previous slide. So if you want for the slide, you can tune out. This slide might not be important. What this slide will show is their main result. So their main result is they say that Hyperband will return high-performing models with minimal training. That's what they claim. I'll walk through what that statement and all the qualifications right now. So the first qualification is will. This is a high probability statement, so it only holds the probability 1 minus delta or something like that. Okay. Then the first big takeaway from this, the bound they show is close to the lower bound, and it's a lower bound on loss, so it's really an upper bound on score. But that's great. That means that there's strong motivation to use this algorithm because it works really well. And there turns out that they only analyze the infinite case, so you can get rid of all the log factors. They also showed they claimed it was simple to adapt to the finite horizon case, but right now we're in the infinite scenario because that's a lot of it. And then if you look at the the time variable t, we see that Hyperband decays like a square root.
Question for you: Is this a part of scikit-learn?
This is not a part of scikit-learn. This is a part of Dask ML, which
a question for you: Is this a part of the scikit-learn Dask ML? Got it. Okay, got it.
Yeah. I think scikit-learn. So I saw Andreas give a talk at Sci-Fi 2020, and I think he said that this was coming to scikit-learn too. It won't be quite as, so yes, so it's coming. Yes. Although it is it is a part of Dask ML right now, and I'll talk about that that's coming. I'll talk about that more in the future, like probably in 2 or 3 slides. Right. Right. So then the point was that Hyperband decays or the loss or the score increases like score of time. Hyperbands or random search, the score increases like 1 to the quarter root, which is not as fast. Okay. Yeah. So during when I was collaborating with Anaconda back in 2018, I worked for Anaconda, who developed Dask. So if you want this implementation of Hyperband, you can pip install daskml and type from daskml.model selection for Hyperband search CV, and you will have Hyperband. You can use it as I'm going to describe in the next couple slides. Yeah. So right. So Dask was a tool to scale Python, to larger data sets or larger NumPy arrays or more computers. DaskML is a tool for machine learning, but has the same goal for machine learning, right? So it's supposed to scale machine learning to larger data sets or more computation. And Hyperband Search CV does both of that. Scales to more computers and larger data sets. Okay. Right. So back in 2018, I implemented Hyperband to DaskML. Turns out Dask can also help Hyperband too. But first, before I mention that, let's look at how to use Hyperbands. And to my knowledge, this is the first implementation of Hyperband in an advanced Java scheduler, like Dask. Okay. So before I walk through each example, I have 2 examples. Before I walk through them, I want to mention the takeaways. I'm going to tell you. So first, Hyperband is a lot better than random search, so it requires less bidding and less time, or less passes through the data and less wall clock time. Hyperband also works with a lot of data types, so it works well with NumPy arrays, Dask data frames, pandas data frames, and the CuPy arrays, PyTorch sensors, all of that. So Hyperband also works with scikit-learn, of course, because scikit-learn is scikit-learn works. It also works well with PyTorch, which is a popular neural network library. And it turns out it actually works with any model that implements the scikit-learn API. And then it turns out so Hyperband is great, Dask is great, but those 2 together enable more performance. The sum of the parts is greater than the sum of the whole, or vice versa. I'll mention that more later. Okay, so the first example, let's walk through a synthetic simulation with scikit-learn. So let's use scikit-learn's MLP classifier, the multi-layer perceptron from the neural network module, to classify some synthetic data set with 6 features. Each of those 6 features will be representative of a class. There will be 4 classes. The colors and the plot represent that. There are 2 informative features and 4 noisy, uninformative features. And let's configure to have 24 neurons. So this could be 24 neurons in 1 layer. This could be 12 neurons in 2 layers. This could be 6 neurons in 4 layers. It could be 4 neurons in 6 layers. Anything that adds up to 12. It can also be 12 neurons followed by 6 neurons followed by 3 followed by 3. And then so that's this first parameter here. That's the only one that controls model architecture. The other, I think, 6 parameters control finding the best model of any architecture. Okay. So now, how do we use Hyperband Search CV? So the documentation recommends that you. So Hyperband also has hyperparameters, right? That models parameters that you have to give it for initialization. Luckily, there's some good intuition on how to do that. So you have to know 2 things. You have to know how long you train each model. So here we're saying you have to train each model, like through 50 passes through the data set, and you need let's sample approximately 300 parameters. Here I show 299 to make the Dask arrays chunk nicely. With those, I can specify the 2 inputs to Hyperband Search CV, this thing called max iter, and the chunk size for each array, which So max iter is determines how many times we call partial fits. Partial fit is called on a chunk size of a Dask array, or a chunk of a Dask array. With those, I can easily create Hyperbands search CV, and then I can rechunk my array to obey the chunk size, right? With that, I can call search.fit, and I see things happen. Of course, this specification of n examples and n parameters didn't exactly specify the amount of computation that would happen. If I want to know that information, I can use search.metadata. But then, after I call search.fit, I can see stuff happen, especially if I specify the verbose flag in Hyperbands search CV. So here, I can see, I can see the Dask dashboard saying, oh, hey, here I'm calling partial fit on, this model, and it's, X% of the way through. I have this many score calls left. I can see which scores were received by Hyperbands if I specify the verbose flag because they're printed to the console. This is great. I can see what's happening, and I can see how long I have left and all of that. And then, of course, this Hyperbands search CV object obeys the scikit-learn API. So it's almost exactly the same as randomized search CV. If you want the best estimator or best params, those parameters are there. Okay. Right. So now, so that's how to use Hyperbands. Now, how well did that work? So here I'm going to compare Hyperbands in blue and randomized search CV pretty much in red, or in orange, I guess. So I'm going to configure these two models, these two estimators, Hyperband and random search, to do the same amount of work, right? So Hyperband does some early stopping, so it can evaluate more parameters. Random search is just pretty much the number of total partial fit calls divided by the number of models of evaluate is a lot less because it doesn't do any early stopping. And we see that Hyperband, at least, so this is the final validation accuracy for Hyperband and random search, and we see that Hyperband is a lot more confident in the result. We find the scores up a lot higher. Like so, every score here is between I think 8 and 92. I think. Turns out the lowest of the Hyperband runs. So this is over 200 independent runs. I change the random state in the random search and Hyperband search. But the worst of those 200 runs perform better than half of the random runs. That's good. And if we look how the scores increase throughout time, we see that Hyperband requires about a third less data than incremental or random search. Yeah, so that's about a factor of 3 to reach 85% accuracy. And then so here I'm showing the mean score across those 200 runs. And the dashed green line is pretty much the time required to train one model. Or it's really the time, or this wasn't run on my laptop with 4 cores, so that's the amount of data required to reach to train 4 models. And all 4 can run in parallel, so this is exactly the time it would take pretty much to train 4 models. This is a very serial environment. My laptop, only 4 workers. So here, pass it through the data set is a good proxy for time resolution. Okay, so basically it's we can find high scores with high confidence if we don't do much work, and we require about a third less data to reach a particular accuracy than random search. That's great. Okay, so now I want to mention the interesting part of this for me, which was so I described how I implemented Hyperparameter in Dask, which is great for Dask, right? It gets a better model selection algorithm. But how does Dask help Hyperbands, right? So the last slide I just showed was pretty much replicating the experiments in the Hyperband paper. But now, what does Dask bring to the table? So Dask allows assigning priorities to different jobs. So if you have 1,000 slots, so let's say, for example, you have 1,000 jobs, and you only have 4 workers to run them on, right? So which of those jobs are you going to choose? So by default, Dask will say first in, first out. So just the first job that was submitted. But you can configure that. You can say this job has X priority. That's great. So why not just say that any model's priority is just the last received score? This will train models with higher scores more earlier, and hopefully that works, right? So I did an experiment with that. So that experiment is shown by this graph. So So the two blue lines, those are one run from Hyperband Search CV on the last graph. This graph, this is the mean. These lines are one run from that mean, from the 200 runs. So everything is the same in those two blue lines except the prioritization scheme. So one says that just first in, first out should be the priority scheme, and that's the dashed line. The solid line says you should prioritize models by how high their score is. And then I show the orange line in comparative search CV just for context. I see that this prioritization scheme matters a lot, probably like a factor of 8 from 400 to 50 passes through the data to reach 80 or 90% accuracy. That's great. Yeah, that's great. So that's how Dask helps Hyperbands. And then I should mention that so this was on my laptop with 4 cores. So serial environments benefit the most from this, right? Because, I mean, if I had, right, because if I was in a very parallel environment, one with an infinite amount of workers, right, then priority wouldn't matter at all. If I only had one worker, priority would matter a ton. So when I have a low number of workers, that's what matters the most. Okay. So now I'm going to go through a second example. So this example will show 2 things. First, it'll show that Hyperparameter Search CV works well with other models, not just scikit-learn models, and it works well, and it will show how well Hyperparameter Search CV scales. So if you want to do it with 32 workers, let's say, it'll show how effective that is. Okay, so first, I'm going to go through the same thing, the model, and so let's use the classic MNIST dataset, which is with handwritten digits. And let's add some noise to the inputs, and let's try to remove that noise from the outputs, right? This is an autoencoder, if you're familiar with that. And so we can build a model with PyTorch. Here I build a model with PyTorch, this file called autoencoder, and then I use Scorch to wrap that with the scikit-learn API. So Scorch is a library that brings a scikit-learn API to PyTorch models. So the important part is that I can use PyTorch with this. It's great. So that means I can build an autoencoder in PyTorch, and then use Scorch's neural net regressor to create a scikit-learn API for that model. It's like that's great. And Scorch is actually pretty easy to use. It's pretty nice. So it works well with NumPy, SciPy, or NumPy, Torch datasets. It can work well with CUDA. All of that. It's a really good wrapper around PyTorch. And then I can have some search space. None of these parameters are super important. The only one that matters is model activation, which controls the model architecture. All the other ones control finding the best model of that the best model of any architecture, or the best model of architecture. Okay. And so I should mention that PyTorch is a popular neural network library. TensorFlow and Keras were more popular in the past, so PyTorch I think has eclipsed them. Or that was true at least last time I looked at Google Trends. Okay, so now let's run this. Let's run the PyTorch model, and let's see how well it scales to a different number of workers. So each of the bars here these are all the same runs. So 8, 16, 24, and 32 workers, they all produce the exact same results on the same scores and all of that. They're all exactly the same, except for the number of workers. The way I did this actually was I wrote to disk and then said that a fit call should sleep for 0.1 seconds or something, and then return the score from disk, or yeah, pretty much that. So what that means is that that we can see how well it takes to finish training a model. And so the solid white line here is the time required to train one model to completion. So I think he's had like 250 partial fit calls, or 243, I think. But we see that the time required to train a model is, so if we only have 8 workers, it takes 2.8 times as long to train Hyperparameter Search CV as it does to take to train one model, right? So it takes 2.8 times longer than it takes to train one model. If we go up to 32 workers, it takes 1.25 times longer, that's actually pretty short, right? Only 25% longer than training one model. That's pretty good. And then if what we could do is we could look at like the ideal speed up. So we expect 8 times to be, or 16 workers to be twice as fast as 8 workers, and 32 workers to be twice as fast as 16 workers. And so it turns out the speed up starts to saturate somewhere around 24 workers. So that means that maybe going to maybe between 32 and 64 workers, you won't see a huge gain. You'll just have more computers for what benefit? Yeah. Right. And so it's basically this. So here are here's a summary of my entire talk, pretty much. So to find the best hyperparameters, DaskML will return high-scoring models with certainty for not too much work. It'll require a third of the data for that randomized search CV, and it'll return the best model in about 1.5 times the time required to train one model, which is great. And so in summary, the one takeaway I have is that DaskML's hyperparameter optimization will find high-performing models pretty quickly. I should also mention that there's some work out there. There's a PR to DaskML right now, actually, that looks at integrating Keras into DaskML. So the dream, actually pretty shortly, DaskML model selection will work with scikit-learn, Keras, and PyTorch. That's great. That's all I got. What questions do you guys have?
There is one question from chat from Nicholas Arquette, and the question is, do you recommend not to bother with grid search? Oh, I guess there's a bunch of questions now, so if you could just go through, can you see them? So maybe you could just.
Well, yeah, so I can, give me a sec. So, I can do that. Pause. Okay. No, pausing didn't work. Well, whatever. Stop. There we go. So the question was about grid search, and so actually I recommend skipping grid search and going straight to random searches. Grid search, and all right, so now why? So grid search requires that you know how important each hyperparameter is, right? So let's walk through a simple example, right? Let's say there's one parameter that controls exactly how important, let's say it controls the final score of it's the sole determinant, it's the only important hyperparameter. But you want to tune another one too, some unimportant one that doesn't matter. With grid search, you'll just run a bunch of repeated results, possibly with the same, right? Like you'll tune one value of an important one and a ton of values of an unimportant one, right? And you'll do that, so what I'm trying to say is that grid search requires you to balance how important each hyperparameter is. Random search just doesn't matter, right? It doesn't matter how important each one is. It just randomly chooses one. Yeah, so I would.
Okay.
Yeah, so there's a paper by Benju and Bergstra called randomized search or something like that, and it walks through some more detail. Oh yeah, I was supposed to go through the chat.
Arun asks, can Dask be used for simpler tasks like for loops and matrix multiplication?
Yeah, absolutely. So Dask, yeah, absolutely. Both of those very, very explicitly. So I use Dask. So I've actually implemented a randomized search CV myself with Dask. That's a for loop, right? Just an embarrassingly parallel for loop. I use Dask for that. And then matrix multiplication is actually one of Dask's primary focuses. So if you matrix multiply 2 Dask arrays, it'll do that very efficiently. You're right. So then Nicholas asked a question about a variety of systems. Amazon, Azure, Yeah, so Dask works with all of those. So if you go to, so if you look at Dask's deployment page, actually, it says it works with like, actually all EC2, Amazon, Azure, Google Cloud Platform. I'm not sure about Windows Sublinux. I'm not sure even what that is. Dask works on top of Windows, if that's what you're asking. It works well with Yarn/Hadoop. It works well with Spark. It works well with Slurm. It works well with SGE. It works with HT Condor. It works with pretty much everything.
And a variety of those systems would have like a Linux, you know. And so the Windows sub-Linux is basically just a better way for you to run Linux machines directly on Windows systems. It's something recent that Windows came out with, so it's much more integrated. It's much more integrated, but it's it's essentially an easier way to have a Linux system on a Windows machine.
Right. So Dask also works well with Windows too, right? So if you wanted to, you could have each Dask worker be on a Windows machine. I mean, OS agnostic. So if you're interested, here's the deployment page for Dask, which walks through setting up on your own machine, on whatever. And so I see your question about, so Nicholas asked a question about CI and CD and Dask ML.
Yeah, so what I'm really saying is that, could all of this code be sort of put into a pipeline? You get new data, you want to run it through this whole entire process, right, of Dask ML. Yeah, like maybe setting up, using Papermill and setting up your Jupyter notebook to pass in parameters. Is there a way to sort of automate what you've developed as a part of, Dask ML and include that as a part of your process, your pipeline, if you will, of like saying, new data, I'm running it through this. Yeah.
So I'm not the person to ask on that. I don't know.
Okay.
I suspect that Dask can fit into those tools, but
sure.
I don't know. I don't know.
Okay.
And then Shiam, I'm not sure if that was correct. You asked about how Dask is different than Jupyter. Can you expand upon that question? Yeah, I guess let's answer it in the chat. Dask is something that goes on top of pandas. Jupyter is something that goes on top of Python.
I also have a question. How is Dask different from asynchronous? Because I had to use I used asynchronous one time for web scraping, and the syntax was actually a little bit familiar when I was seeing like the Dask tutorial. So are they different? Are they the same, or are they like what are they?
So they're, I guess, separate. Yeah, so they're tangential, I guess. So Dask can be used with async functions just fine. Actually, most of the Dask code is written with async and awaits. Yeah, so you can use async functions with Dask. You can await Dask functions super easily. Although async and await also works well on your own machine too. So I guess Dask is a well to scale Python, and part of Python is async and await.
Cool, thanks.
Yeah.
Hello, can you hear me?
Yeah, I can hear you.
Yeah, I'm here. Okay, so I understand I have to import Dask into Jupyter. Is that right?
Yeah, you can do that.
Okay. Are there any special installation instructions, or just this pip command is okay?
So Dask is pure Python, so pip will work just fine.
Okay, thank you. I never done this, so thanks. I'll try.
Yeah, you bet. I mean, you bet.
And would you still think about using some of the faster methods instead of using, pandas directly, such as using NumPy or Numba? Like, how does that? Would we still sort of take those considerations while working with Dask?
Yeah, I mean, so
like we know that a certain thing takes a smaller amount of time. Use that best approach.
Yeah, so all Dask does is just it maps NumPy like so a Dask array really is just chunks of NumPy function, chunks of a Dask array is made up of NumPy arrays, right? And all it does is it brings those NumPy arrays to functions, right? So that function can be NumPy compiler just fine, right? It'll still work. You'll see a benefit there too. From like yes, so it works well with NumPy. It works well with yeah, it works well with NumPy too, I guess.
Do we need to import Jupyter Torch? Sorry, PyTorch?
You if you want to use PyDrives with Dask yeah. That so a good page is Dask's example page. So here it walks through how to use Dask. I have a bunch of Jupyter notebooks pretty much online.
Okay.
I put a link in the chat.
All right. Okay. Thank you.
Yeah. And so I think the example on hyperparameter optimization with Dask, I think that walks through an example with PyTorch.
Okay.
No, this is scikit-learn. But if yeah, maybe I should put an example on here with PyTorch. I should probably do that. And then Nicholas asked about, is this available in Google Colab? I suspect. I haven't used Google Colab, but I think if you do, I mean, it comes with Anaconda by default, right? So it's probably in Google Colab. If not, you can probably just bang pip install it. I'm not sure how to install things in Google Colab.
Well, awesome. That was super great. And
Cool.
yeah, learned a whole lot.
Yeah, and if you have any more questions, I guess you can shoot me an email. I'm not sure how else to do it. Or you can reach out to Liz or Pablo. They can reach out to me. So Nicholas asked one more question about Docker. So there's a GitHub repo called Dask Docker that has Docker images that specially install Dask and Docker machines. They even allow for the installation of custom packages too, so it's great.
Awesome. And then when we're looking at your slide talks, you said /talks. Go to your GitHub repository in talks.
Oh,
Which
yeah.
one is it specifically hyperlink? Is it going to be there, or is it already there?
It's already there. I gave a talk back in I gave a talk at Sci-Fi 2019, I think. So it's
Yes, that should be that one. Okay.
Yeah. So I just sent a link across too.
Cool. Thank you.
Yeah.
Great stuff.
Okay. Thank you so much, Scott.
Yeah.
It was an amazing, very informative talk, and I personally think that I may use this sometime because I used to work with scikit-learn and random grid search, but this seems to be very easy to integrate and adapt. Actually, I thought that it was more complicated, so I never even tried to use it because I thought that it may have a steep learning curve or something like that, but it seems like it's pretty easy to integrate anywhere.
Yeah, so I discovered Dask back in 2016, and I had the same experience. I was like, wow. So I was running some embarrassing parallel for loop, and I was like, wow, this is easy to use. So to use it actually, so maybe I should mention that. So I had some hyperparameter search. I want to make some graphs, some grid search, I guess, and I had to run. I had 25 parameters I had two different parameters. I wanted to evaluate 25 for each, and then evaluate each of those for 10 random seeds. So I had it's like a 250,000 jobs or something. When I changed, to deploy that on the optimization, the cluster I have downstairs at my place of work, I changed 2 lines and added one, and ran one command on each machine, and then boom, I had access to 640 cores. It's like great. I can run across 600 machines super easily, almost hopefully.
Yeah, it's incredible.
Yeah.
Yeah, it's very cool. So, Alisa, do you have anything else to say?
That's all I got. Oh yeah, go ahead.
Oh, I was going to say just very briefly, we also have our next speaker or speakers lined up. They are two people that I went to grad school with, and so they are both very excited to give talks. So I just wanted to mention that for everybody who's still hanging around, and to keep on the lookout for a announcement about that. But other than that, I wish I had heard this talk last week, because I'm literally going to go and use Dask right now for a project that I'm working on that I literally need it super bad for. I was just like, perfect. So.
Nice. I mean, Alyssa, if you need help, reach out. I mean, yeah, that's nice. Thank you.
Sounds good. Yeah, we'll do. Great.
Pretty amazing.
Yeah. All right.
Thanks, Scott.
Yep. Thank you.
Thank you,
see you guys
Scott.
around. Thank you.
Cool. All right. Bye-bye.
Adios.
All right. Bye-bye.